Good morning, Astronomy 1010. Welcome back to our sixth lecture, or I guess we're just having half a lecture this week because we just had the midterm exam, which you guys suffered through on Monday. I want to talk about the exam a little bit. I have not graded it. Now that you take the test on Blackboard, I don't actually have to grade it. Blackboard does it for me. But I still have to go and I have to look at all your grades and compile them in my spreadsheet because today midterm grades are due. And that means by the end of this workday, like 5 o'clock, I need to take your grades and I need to compile a midterm average letter grade of how you're doing so far. Even though I submit them today, I think they have to roll over at midnight before you can see them. So I expect you'll see your midterm grade on the My CCRI page tomorrow at the first time. But even though it will kill a few minutes of class time, I thought I could talk about how I compute that midterm grade so you can understand what I'm doing. And that'll give you a little more transparency and maybe make you feel better if you didn't do so hot in the test. So let's take a look at the board here where I'm going to review how your grade is determined. So for your midterm grade, and this is your midterm letter grade, not the midterm exam grade, I'm trying to use a rubric that follows this, this logic. Homework, your total homework score is worth 25% of your grade. Lab, 25% of your grade. And when we eventually compute a final letter grade for you, your midterm will be worth 25%, and your final will be worth 25%. Now, up to this point, all I have are scores for this, and this category, but I have no idea what that's going to be. I can't simply take an average of these three percentages, because if I did that, they would each get a 1/3 or 33% weighting, and that will artificially inflate the value of homeworks and midterms. Homeworks and labs. So I can't just simply take an average of what you have so far. Here's what I'm going to do. I am going to propose or assume that you will get the same score on your final that you got on your midterm. Now, that doesn't have to be true. That is up to you. But I don't have any other information to work with, so that's what I'm going to assume. And by the way, it usually works out that people tend to score within 5 to 10 points of their midterm grade in their final. It's usually actually pretty consistent. Not always. Okay, so let's just look at a hypothetical student, okay? And let's call that student Bob, okay? Now, let's say that Bob is like one of the smiling faces that I see out here, like Jenna or Kim or Jonathan. And you guys are people I interact with every week, so I tend to think of you as people who turn in all your labs and homeworks because you've spent the time to sit here with me during these little live sessions. So I'm just going to assume that Bob is a good student who comes to class and does all of his homeworks and labs. And that means I think you've only had about 4 homeworks. So 25 times 4, 100 out of 100 points will give Bob a 100% on his homework score. And I think maybe we've had 5 labs. So 50 out of 50, Bob has 100% on his lab. But let's say Bob's not the best test taker and this kind of stuff is stressful. And let's say Bob gets a 50 on his exam, all right? So his exam score is a 50%. Now, you would assume that 50 is not a good grade on the test. But in my test, it's not terrible, okay? Now, I don't know what Bob is going to get on his final, so I assume that Bob is also going to get a 50 in his final. And now it's time for me to compute his midterm grade. 1 plus 1 plus 1 means that Bob has 3 out of a possible 4 points for a total midterm score of 75%. And now I'm going to apply the astronomy curve. This is the curve that I've decided is appropriate for this course in this class. And in this class, I peg B minus. Sorry. to, I believe, what is it? It's 65%. And I've done that because I've taken the average of many different groups over the years, and I found this is a fair curve for the type of material that you guys are doing. Since a lot of you don't have experience with physics and astronomy before, this can be a little bit of a challenge your first time around. So I go in 5-point increments from there. B is a 75%. Oh, sorry, B is a 70%. B plus is a 75%. A minus is 80%. Anything over 85% is an A. There's no such thing as A plus at CCRI. Then there's C plus, 60%. Since we don't do C minus, I assume that the ground floor for C goes all the way down to 50% to help the people who struggle. D plus is 45% and above. D is 40%. And EGADS, if you're under that level, then you failed the course. And luckily, the only way you can really get to that kind of a level is if you just consistently, obstinately flake on my course and don't do homeworks and labs. I mean, that's the #1 way to fail. But if you just do this 2 parts, there's no way you can fail. I've made it that way. Bob, for instance, got a 50 on his test, but his grade is a B plus. I think B plus is a respectable grade. Sure got my fair share of those in my day, okay? B's get degrees. Never forget about that. Hell, C's get degrees, okay? But B's get degrees. Anyways, this is fine. So you don't have to get 100% of my test to get a respectable grade. What you do need to do is your homeworks and your labs, and then you need to try. And I think each and every one of you are capable of doing that. Am I right? Of course I am. Okay. I have no choice. I'm in charge. Okay. So do you guys have any questions about that before I proceed with today's lecture? I need to cut my hair. Do you have any questions? All right. I hope that helps put your mind at ease if you didn't get the grade that you wanted to get on the test. Okay. Doesn't matter. You just do the test. It's going to be fine. All right. Let's do some work.
I have a question actually. Not
Okay.
that just popped up.
Yeah.
Last class we did the exam prep.
Yes.
Was I supposed to submit that for the homework?
No.
Okay.
That was for you, all of you.
Okay. I just wanted to make sure because I was just like going through what I submitted. I was like, wait, I didn't do that. Was that supposed to be done? And so that's good that I
right. There are some people who I would expect to have stuff turned in that didn't. You know, one of the things about them giving me 28 students per section, and I'm teaching 3 sections of AS1010 alone, is that that's a lot of damn people to keep track of. So it becomes, even if I know you, Nori or Kim or Ian, because I see your faces all the time, it can still be hard to keep track of who's missing what and to let you know about it.
Yeah.
So I would make sure that each and every one of you today goes through your grade center for the class and make sure that you've got your stuff turned in. Sometimes people think they've turned it in, but it gets caught up in needs submission in progress status. Remember that happened with a few people here? Just could you please, it would help me if, and it would help you if each one of you guys could try to keep track of that. So you can say, hey, B, I thought I submitted this, but it's caught in the fucking time loop here. And then we can work it out, okay? All right. All right, cool. So last time we left off, we were talking, or we were about to talk about temperature. We had a big lesson on energy. Today, we're going to do temperature, we're going to do atoms, and we're going to do a little basic stuff about light. And then today, because it's a Wednesday, we're actually going to do a homework number 5, which is the one that we should have done last week. And that's what you're going to be turning in. Sound good, Nori?
Mm.
Okay, nice. And let me just make sure that I haven't screwed that up. The homework 5 should be the next one in our sequence, right? This one right here. Yes. Can you guys see what I'm doing? No, you can't. Okay, it doesn't matter. Homework 5 is next. Okay, let's take a look at the blackboard together. I have a lot to do, and I'm already starting late, so I want to kind of do the temperature thing really quick. let's talk about temperature versus heat. These are two terms that are used interchangeably, but in science, in a technical context, they don't mean the same thing. And the nuances tend to matter in this class, okay? Heat is a transfer of energy, and it's a transfer of energy from point A to point B. Point A could be some whiskey, and point B could be some ice cubes, okay? I know all about that one, okay? Anyways, when energy is transferred from place to place, it's done so using units of joules. I should have asked you guys that as a thought question. The units of heat transfer are the joule, or whatever other, you can transfer heat in calories or electron volts, whatever your favorite unit of energy is. And it's you know what it is? It's a delta E, a change of energy from one place to another, okay? It turns out, and this is going to be kind of important for all the science you're going to be learning in this class, there's only 3 ways to transport energy in nature. Of all the different forms that energy can take, from energy in your muscles to chicken wings to push-ups on the ground, there's only 3 different ways to transport energy. And these are sometimes known as the 3 modes of heat transport. I prefer to say the 3 modes of energy transport to remind us that heat is just basically energy. With time, I'm going to require you guys to know about all 3 of them. They are convection, conduction, and radiation. Radiation meaning light, not particle radiation. Actually, I suppose particle radiation could be a form of heat transfer as well. That's it. You can't transport energy except by one of these 3 ways. Now, I've discovered when I talk to students, they have muddled ideas about these 3 things. With time, we're going to have very clear ideas about them to understand how planets work. But let's deal with that at a different day. For now, I'm just teasing you with the idea that there are 3. Knowing about this is more than just astronomy or planetary science. This is about being an educated person, knowing about convection, conduction, radiation. It's hard to live your life without knowing those things. All right. Let's talk about temperature. Temperature is not the same as heat. And one reason I know this is because I know what temperature it takes to cook a turkey on Thanksgiving, right? Actually, I have some vague ideas about that, but I think if you want to slow roast your bird, you might do 350 Fahrenheit, and you might leave it in there for a whole bunch of hours during the day for the turkey to cook. You can put your hand really quick into a 350-degree oven and pull the turkey out without burning your hand. But if you boil turkey in water, what temperature does water boil at? Do you know? Who knows some stuff about life?
100 degrees Fahrenheit.
False.
Oh, okay.
Sorry. You've got your scales mixed up, Ian. It's 100 degrees Celsius. What's boiling water in the Fahrenheit scale?
Oh, yeah.
Nobody? No?
150?
No, much higher. 150 is the temperature you want to cook.
198.6 or something like, or one. What the hell was it? I'm throwing 15 years of cooking out of
212 degrees Fahrenheit is boiling water. I think Nori was thinking of the temperature you have to cook meat to kill salmonella. I think that's like around 150 or 160 Fahrenheit. Anyways.
I was thinking of like, oh, so I work at Chipotle. This is so funny.
Okay.
And we blanch the jalapenos in boiling water. And I'm so stupid. I don't know why I didn't know this. It's like 202 to 212. I don't fucking know. I didn't say that.
That's
sorry.
Okay. Well, the funny thing about learning is then you start to connect it with your life experiences, and that's good.
I also used to work at Chipotle. Fun fact. So I was thinking similar.
Who's the
All right, fun-
which Chipotle do you work at?
Sorry.
Which Chipotle?
The Smithfield one. At the crossing.
I forget what Morocco his first name is. He's a general manager. I think it's the one on Route 2.
Not familiar, but
Fun
sorry.
fact, my ex-girlfriend loved Chipotle. Like if I drove by one, she would shout and scream and bang the windows of the car. It was a little intense. Okay. It was like, I didn't get it. But hey, maybe I got to give it a try.
It's good. It's good. I like
Yeah.
Chipotle.
I hear it's like pretty fresh.
It is actually pretty good.
Pretty fresh ingredients for as far as it goes. Okay. Anyways, so now you know why that dial, Nuri, says 202 to 212, right? That's the temperature of boiling water. We're going to make a chart in a second. Isn't that strange, though, that you can put your hand into a 350-degree oven, even a 400-degree oven, and you don't get burned? But you wouldn't dare, Nuri, put your hand into that boiling vat of water without protection, right? Not even for a quick second. How can it be that the oven that's at a higher temperature won't burn you, but the water at a lower temperature will? I thought, the hotter it is, the more you get burned. Is it that simple or what?
If I remember correctly from like science class in like 8th grade or something, isn't it probably has something to do with the fact that air versus water or gas versus liquid, where it's a higher concentration of the particles in the liquid.
Yeah.
So a higher concentration of the energy.
That's right. So well, the better way to say it is it's about how much heat can be transferred. It doesn't matter how hot or cold something is. What does matter is how much heat is being transferred to your hand. That's what burns you. That's what makes you feel hot or cold. Temperature oven itself does not always make you feel hot or cold. It depends upon the density as well as some other things. Let's talk about what temperature is. And we could do so by thinking about the water molecules in your vat of water, or maybe even we could think about the air inside of an oven. Okay, so my flash animations are dead now, which really makes me sad. But I should have a crappy little thing here on my slideshow. Hold on, I got
only the best, Teach.
Say that?
I said only the best.
Only the best. Only the best for you guys. But sometimes your best is what you have. And that's what I've got. Function F522. Here's a little animation, which I hope looks smooth over the internet, showing you what could be the particles of air inside of an oven as you cook a turkey or something, all right? And the air that you breathe, we're going to study it later in planetary atmospheres, is made up of 77% nitrogen molecules and 21% oxygen molecules. So you can think of the blue pellets as being nitrogen and the red pellets as being oxygen. And they have pretty close to the same mass. They all kind of function like little BBs bouncing around in a box. And when they smash into each other, or when they smash into a leg of turkey, they transport or transmit momentum and energy into each other during collisions and into turkey legs during collisions. That's how you heat up and crisp a turkey leg in the oven. You're smashing little BB pellets of air into it and transferring energy, which heats up your turkey.
Like
now,
radicals.
the trouble, oh, sorry, Jonathan?
I said almost like free radicals.
They're like, well, different than free radicals, because free radicals have electromagnetic attractions associated. These particles are completely neutral, Jonathan, or mostly neutral. For a gas to behave as an ideal gas, there can be no strong intermolecular or interatomic forces. The atoms have to essentially function like BBs or pool balls that are just smashing around in a box. In other words, we know that they're going to act like billiard balls and travel in a straight line until they smash another particle, and then their collision will be collision-based, not magnetic forces-based, something like that, okay?
Makes sense.
All right. So if you try to follow the speed of any one particle, you discover that it's constantly changing its speed. And therefore, if you try to associate an energy with it, you would associate kinetic energy, because that's the energy of motion. And if the speed is constantly changing, then the kinetic energy of the particles are changing. But collectively, the ensemble of particles should have a total energy which is, on average, constant, because energy must be conserved. This is what you are measuring when you measure temperature. You are measuring the average kinetic energy of a system of particles. Let's write that down. The average kinetic energy.
I have a question.
Yeah.
So potential energy is just like the energy that's like being held in the object until it's like.
Not necessarily in the object, but it is a stored, you are correct in saying it's a stored energy. Remember, Lori, when I picked up my kilogram doodah, where's my kilogram doodah? Here it is. Okay. When I held my kilogram doodah in the gravitational field of Earth, it is a stored form of energy, but I would not be so bold as to say the energy was stored in the doodah. I would say it's stored in the system of doodah plus the height plus Earth. So that's, I just wanted to make a slight correction there. But otherwise, yes, potential energy is stored.
And kinetic energy is the release of it? Is that what that is? Or am I not?
It's moving. It's energy associated with moving particles. For instance, you have to look at the formula. In a way, as you get more sophisticated in science, you have to look at the formula to understand what it is. Kinetic energy, the formula, which we learned last class, is 1/2 times the mass of a particle times its velocity squared. And what that says to me, Nori, is that it says to have kinetic energy, I need to have an object with mass, like this steel ball bearing, and it needs to have a velocity through space. And the energy is the energy associated with a moving particle. A moving particle. Like a musket ball in the Revolutionary War has kinetic energy, because you fire it out of your musket and you hit the British artilleryman in the head, and that's how you transmit kinetic energy to your nemesis. All right. Okay. So anyways, so it's not a release. It's a moving object has kinetic energy. In a way, Nori, all of those little BBs that we were looking at inside the oven of nitrogen and nitrogen and oxygen molecules, they're kind of like little musket balls, and they have their own kinetic energy associated with them. Now, you can still say it's stored, say, in the oven, in the collective motion, but the microscopic detail is of a kinetic energy.
Would it still have potential energy because it didn't touch anything, or would it not?
You know, learning physics, what's so fun and cool about it is physics is just a bunch of lies that we tell people, and because they can't handle the truth. It turns out the truth is wicked effing complex. Like so complex that if I tried to just go and spit it all out at you at once, it would be this cacophonous, confusing din, and you wouldn't make any sense of it. So what we do is we tell you little pieces that sort of seem like the truth, and then as you become more comfortable with them, we unravel the onion skin a layer deeper, and you find out that everything we told you before is a lie. Okay, so right now I'm going to lie, and I'm going to say there's no potential energy in the molecules. Of course, in reality, molecules are connected by vibrational forces, like even a diatomic oxygen atom. These should be the same color. The two oxygens share their electrons, and so they're kind of like bound on a little spring. And those oxygen molecules are actually vibrating. So they do have an internal potential energy. In an ideal gas, we make a point of pride in saying, let's not worry about that yet, because that's going to complicate the picture. Let's treat each vibrating molecule as if it was a stupid little BB, and it bounces off another stupid BB. And believe it or not, the equations that describe an ideal gas do a plenty good job for gases in your oven. So it's a perfectly acceptable lie to tell you. In other words, yes, they have potential energy, but we're not going to talk about that, okay? But I couldn't help myself in suggesting there might be a layer below what we are learning. Or above, I don't know. Anyways, let's talk about how we measure temperature. Obviously, you can't go into the oven and count the speeds of all the little particles because there's just too damn many of them. But you don't need to actually know the microscopic picture of temperature to measure it. All you need to find is a thingy that will change with temperature, and that can be your thermometer. For instance, it could be the height of mercury in a glass tube, or you know those ones that you see on your Grammy's porch. They have a little spring and it turns the needle to what temperature it is outside. Those are different things that change with temperature, and then you create a scale. And of course, we're familiar with the Fahrenheit scale in the US, but if you're cool like Valentina and you grew up in Argentina, yeah, Venezuela, sorry. If you grew up in Venezuela, like Valentina did, then you might use the more elegant Celsius system, which is hard for dummy Americans like us to wrap our minds around. I have a way to do this, which is rather than use the formula, which is boring, it's actually pretty simple to make a little chart. And I'll show you the slideshow that we're going to base the chart off of, just to give a couple of reference temperatures in Fahrenheit and Celsius. Ironically, this might be helpful for you, Valentina, in wrapping your mind around the Fahrenheit system. Who knows? Depending on how long you've been here, you may be still more comfortable with Celsius. Here we go. So somewhere in this slideshow here, we're going to just make a little reproduction of this temperature scale here. So why don't you guys play along with me in your book? Let's do it quickly because time is of the essence. We'll be discussing temperatures on planets in Celsius very often, so this will be helpful for us Americans here to have this. And it's actually helpful for me too. All right, make 1, 2, 3, 4 columns. I like making tables of things. Okay, how's my focus? Does it look okay? All right, so this will be the substance. We'll do degrees Fahrenheit, degrees Celsius, and of course, one of the purposes of this lesson is to introduce a new temperature scale. The official metric units of temperature that we use in science are the Kelvin. Let's do one for boiling water, human body, room temperature, freezing point of water, and we'll keep one column at the end, okay? So we'll do boiling water, human, room temperature, freezing water, I'll save the last one there. So you guys know water, I hope, freezes Valentina in the Fahrenheit scale at 32 degrees Fahrenheit, okay? Most people tend to know that temperature because it means pain when they see it on their phone, okay? Boiling water, we have since learned, is 212 degrees Fahrenheit. A human being is around 99 degrees Fahrenheit. And room temperature, the standard room temperature is around 68 degrees Fahrenheit. Although mine's set at 72 because, you know, I like a little extra comfort. Anyways, these are sort of standard numbers that you come across. The Celsius scale is a bit more elegant in its design. I forget the deal about how Fahrenheit came to be, but it's older than Celsius. And I think the original idea was that humans should be 100 and water should be 200, which is kind of stupid if you think about it, because humans are not reliable, measurable device. There's actually fluctuations in body temperature. The Celsius scale was designed to use only one substance, water, which is convenient because most people have access to water. You have to or you die. And that means everyone has a sort of substance they can measure for changing temperatures. So in Celsius, we set freezing water to 0 degrees Celsius, boiling water to 100 degrees Celsius. Room temperature is around 20 degrees Celsius, and a human body is 37 degrees Celsius. Did I do that right? I would ask Valentina, but I don't see her there. Let me just check my cheat sheet. Yeah, okay. The idea behind the Kelvin scale, well, first of all, when the Fahrenheit and the Celsius scales were developed, we actually did not really know what it was we were measuring when we measured temperature. We measured something as hot or cold as perceptual experiences. But through careful study of gases, John Boyle, and some other famous scientists slowly pieced together the picture that I shared with you, this picture. A picture of particles bouncing around in a box. Now, the scientists who first measured temperature, they used gases to study temperature and discovered that they were basically measuring the speeds of a bunch of little particles. But you should realize that even if you're dealing with water molecules, or if you're dealing with a solid, you still have the same situation going on. In a solid object like a block of metal, you still have atoms that are kind of connected by intermolecular forces. They kind of act like little springs. And these particles still have temperature and kinetic energy. Oops, sorry, let me clear that. Because they can be kind of vibrating and bouncing around in place in complicated ways. So they're sitting there jiggling and vibrating on those springs, and those motions still have kinetic energy and they still have temperature associated with them, okay? When you touch a hot rock in the desert sun, you feel the heat from those jiggling atoms touching against your skin, all right? At some point, as we cool a substance, the particles will move slower and slower and slower as their kinetic energy is reduced. And the people studying these gases and understanding temperature realized if you extrapolate the graph all the way backwards, there should eventually come a temperature at which all of the kinetic energy of the particles stops. And this would be this hypothetical place where all motion of particles would go to zero. You guys know what that's called?
Absolute zero?
Yeah, that's right. Absolute zero. And absolute zero occurs at a temperature of negative 460 degrees Fahrenheit, negative 273 degrees Celsius. Lord Kelvin had an idea, which is, you know, the Celsius scale is a really nice temperature scale, but it's silly to have negative temperatures when it's inherently a positive quantity that we're measuring. So basically, Kelvin is the same thing as Celsius, but the only difference is that you shift the 0 point to absolute zero. So 0 Kelvin is absolute zero, and that means freezing water is positive 273 Kelvin. Boiling water is 373 Kelvin. A human body is 310 Kelvin. And I think room temperature is 293 Kelvin, if I did the math right. My idea is that whether you're coming from a country that uses the Celsius system or Fahrenheit system, we're all going to have to use Kelvin. And this is a cool way for us to be able to relate to each other, just some basic temperatures. So it's a nice chart for your own personal lives to kind of accidentally memorize. I've got a plan to try to adapt myself better to the Celsius scale. I think I want to change my phone temperature to Celsius so it just becomes like second nature to me. That's a thought I've been having, but I haven't actually gone there yet. Okay. You guys have that? I'm going to erase now. Let's talk about atoms. Speaking of water at 32 degrees Celsius, this is tasty stuff. All right. Let's talk about the Bohr model of the atom. We've got to do a little review to make sure you guys know some basic stuff about atoms before we go any farther. How many people here have had to take a chemistry class before? I want to see what I'm working with. Ryan, Jenna, that's it? Ryan, Dick has, Kim as well. Okay. So some of you guys have been exposed. Zachary, good to hear from you too. All right. you don't have to be chemistry master. We just have to know some basic stuff, okay? And let's make sure we can all get on the same page. Let's talk about the second most famous element on the periodic table. Let's make a little model of the helium atom, okay? A helium atom has 2 protons in its nucleus. Protons are, of course, positively charged. 2 neutrons in its nucleus. And provided the helium atom is electrically neutral, it will have 2 electrons in orbit around the atom. This is the second most basic element in nature. It's called helium. And let's just label our parts to make sure that we understand some things, okay? So this little bugger here is called a neutron. This is called a proton. These guys up here are electrons. We'll define them in a bit. Taken together, neutrons and protons make up the nucleus of an atom, right? So this part of an atom is the nucleus. Sometimes you want to talk about the total number of particles in the nucleus. Like, for instance, this nucleus has 4 particles, whether we consider them positive or not. And for that reason, we can sometimes use a term to describe either neutrons or protons. We call them nucleons. Nucleons can be either a proton or a neutron. That's a convenient term to know about. What makes the Bohr model of the atom Bohr-like, after Niels Bohr, the guy who kind of came up with the concept, is the Bohr model of the atom functions superficially like a little baby solar system, with electrons in Keplerian orbits around a nucleus. Now, if I were to ask you guys, what makes the Earth orbit the sun, you would say what? Why does Earth orbit the sun?
Gravity.
Right. Why does the electron orbit the nucleus?
It wouldn't be gravity.
It would not be gravity.
Yes.
Although there is microscopic amounts of gravity here, these particles are insanely low mass. The mass of an electron is 9 times 10 to the negative 31 kilograms. With that microscopic of a mass, the electron does not feel any sufficient tug towards, I mean, think about it. Hell, you don't feel a force of attraction between these 2 markers if you hold them in your hands. So for electrons are a bazillion times less massive than these guys. They're not going to feel any force.
So it's not magnetism, is it?
It is. It's the force of electromagnetism. And this is the second fundamental force that you guys have had to learn about in this class. So I want to take a moment to go, oh, all right.
Isn't there a little machine that you can make with positive and negative electrons that you can see the move air move?
I'm trying to
I know
think.
they were talking about that in space for the longest time because there's no gravity up there, that they can bounce positive and negative neutrons up there like a microwave, and they can cause thrust.
Wait, some of the stuff you're talking about, there are no positive and negative neutrons, right? Neutrons.
Okay, yeah, that's what I mean. So I'm probably confusing something I read with this.
Well, if you find that, send it to me, because I'm curious as to what you're talking about, but I can't get a thing on it. There are lots of ways to watch air particles move around. I mean, you can use infrared cameras and do sort of like high-speed photography. I can show you some cool stuff. Like when they study the motion of supersonic bullets through air. Let's talk about electromagnetism for a second, and that will help us clear up our discussions. So we can say that atoms are held together by a fundamental force, the force of electromagnetism. Electromagnetism is based on a property of matter that is not mass, but electromagnetism is based on a property called charge. And charge can come in three flavors, right? Positive, negative, or no charge. And the rules of electromagnetism are more complicated than gravity, but they're not overly complicated at first. There are two rules. The first rule is that like charges repel. And the second rule is opposites attract. So basically, if you've ever spent time goofing around like I have with some basic refrigerator magnets, then you know how this is supposed to work, right? Magnets are also related to electromagnetism, obviously. But although the magnetic force is a little more complex to explain, and I will be explaining it over time, for now, you can pretend that if you have two magnets north and south together, that's very similar to the attraction that a proton and an electron would feel. And of course, if you've ever taken the two north poles of a magnet and tried to push them against each other, you can feel that magical invisible force. This is as close to magic as you're ever going to get right here. And that's why I think electromagnetism is so cool. You can feel this invisible force field. You can't see it, you can't taste it, but egads, it's there and it's effing powerful, okay? Electromagnetism is the second most powerful force in nature. In my other class, I actually have the students do a calculation where they compare the force of gravity between two electrons versus the force of electromagnetism between two electrons. And the force of electromagnetism is, I kid you not, 10 to the power of 42 times stronger than gravity. That's not like a million or a billion or a trillion. That's a kabillion fuckload, okay? That's just a stupidly big number, 10 to the power of 42. For example, okay, the number of seconds in the universe since the Big Bang is like 10 to the power of 20. So that's 20 orders of magnitude greater than the number of seconds in the universe since the Big Bang. That's a big number. Electromagnetism just totally overpowers gravity. Whenever it's electromagnetism versus gravity, electromagnetism wins. And in a weird way, that's why you have so much less experience with electromagnetism. Because electromagnetism, as Hunter S. Thompson says, is mean and violent, and it wants to kill you. And we tend to find substances in nature that are not imbalanced in charge. Things tend to be electrically neutral because when they get out of balance, some really crazy violent shit happens, like lightning bolts, as nature tries to correct the problem. So these things are so extraordinary because this represents a place where nature has allowed charges to become temporarily unbalanced. And egads, do you get a big result, okay? For this reason, most atoms tend to be electrically neutral, but we're going to study many situations in physics where electrons get torn off, all right? Now, I need to do some basic stuff, some definitions before I go forward. Can I erase all this, kitty cats? Are you good with your helium atom here? Okay. By the way, I'd like to remind you guys, you probably have never learned that comparatively in terms of size and mass, protons and neutrons are big fat particles with roughly the same mass. And the electron, by comparison, is a little tiny microscopic particle. Now, it's weird that in nature, boy, why is this fuzzy? Proton, maybe it's just the red. Looks
The
fuzzy.
Scotch talking.
Huh?
I said it's the Scotch talking.
No. Wait, I hope it could be. I hope not. Does that not look fuzzy to you guys?
The red looks a little bit faded, but everything else looks fine.
Okay, all right. Maybe it is the Scotch talking. Anyways, It's important to recognize that protons and neutrons have about the same mass, and they're roughly 2,000 times more massive than an electron. And that means nature has a really perverse sense of aesthetics. Why would nature make a big fat particle whose positiviness is equal but opposite to this little microscopic particle with negative charge? In other words, their masses are super asymmetrical, but the negative charge here perfectly cancels out the positive charge there. That's like a weird kind of lopsided design. And people have often wondered about that. It turns out there's some cool stuff behind that. It has to do with antimatter. It's possible for nature to reverse this procedure and make big fat particles with negative charge and little tiny particles with positive charge. And we actually create antimatter inside of these atom smashers all the time. More on antimatter never. Okay. Anyways, let's define a few things about atoms that we need to know. Let's start with A, what I'm going to call the atomic number. The atomic number is the most important number associated with an atom. And it basically just tells you the number of protons in the nucleus of the atom. Why is that so important? Because we have decided that the atomic number, the number of protons, defines the atom or element. Same thing. As we start adding neutrons and subtracting electrons, things are going to get confusing. If we always define the atom to be the number of protons, we will stay sane. For instance, I could introduce you, if I was feeling generous, I could introduce you to the ye olde periodic table of the elements, the totality of all the atoms that are known in nature. And each atom differs from each other atom by the number of protons in the nucleus. So you can see the atomic number up here. We just studied helium that has 2 protons, okay? Next up, let's define something called the mass number. The mass number tells you the number of nucleons in your atom. That is, to remind you, the number of protons plus the number of neutrons combined. The reason why the mass number is important is because the mass number defines not only how massive the atom is, but it also defines what is known as the isotope of the atom. An isotope means same number of protons different number of neutrons. And in nature, isotopes abound. For instance, if we look at our periodic table of the elements again, you can see the mass numbers. Okay, this is actually a pretty crappy, well, it's just a hard to read periodic table of the elements. Why don't we instead go to my favorite one that I used as a chemistry student in high school, and that's the ye olde Sergeant Welsh periodic table. This one is full of tons of info, and you're going to see me using this all the time. Let's filter by large so that we can really get in there and see this thing. I think this was pretty good. Oh yeah, excuse my yawning. 3,000 pixels. I can do that all day. All right. You guys can see that the mass numbers of atoms, like iron, for instance, are fractional, because in nature we find different types of isotopes. What 55.8 tells me is that there is probably an iron 55, and there's probably an iron 56. And iron 56 is the more common isotope because the average is closer to iron 56. So iron 56 would have how many neutrons? 56 minus 26 is 30. So your standard iron atom has 30 neutrons, but there are isotopes with 29 neutrons in it. And so here you can find the mass number. And it defines our isotopes. Isotopes are important. I'll give you some examples in a second. Lastly, but not leastly, we could talk about the number of electrons. Most atoms are electrically neutral. When an atom is neutral, it has no net charge. It has the same number of protons equal to the number of electrons. That's when atoms will behave essentially from a distance like a faceless BB with no net charge to it whatsoever. It is possible to take away electrons or to add electrons using violence. And when you use violence to alter the number of electrons, you then get an ionized atom. An ionized atom is when you remove, or in some cases add, an electron. A collection of ionized atoms is known as a plasma. A plasma is a charged gas in which electrons have been removed from the atoms and bounce around with electrical and magnetic forces affecting them. Plasmas are wild and cool and crazy. When we study the sun in a little bit, you'll get to see some pictures of plasmas in action. If you've been to, what is Spencer's gift store still around? If you've been to Spencer's gift store and you've seen one of these things, that's a plasma. That's a high temperature gas in which electrons have been removed from atoms. We can talk about this plasma ball sometime. Okay, you guys got that? Does anyone, you guys seem to be pretty fast at the notes, so I'm ready to erase if you're ready. I got more modules to do today. I'm doing okay. All right, I think I'm doing okay. Let's take a moment to make sure you really got that, okay? Now it's time for us to play a game that will prove to me that you understood everything that I just said, okay? So this game is called Let's Build an Atom, okay? And my first atom, atom number 1, is going to have an atomic number of 1, a mass number of 1, and it will be electrically neutral. Who can tell me what to draw if I want to draw that atom?
It would be just one proton with one electron orbiting it.
Correct. So let's show what Ian just said. One proton, that takes care of your atomic number. Your mass number is 1 nucleon, and Ian recognizes that he's already used up his 1 nucleon, so he doesn't add any neutrons. And electrically neutral means you have to have the same number of protons and electrons. Boom. And do you know the name of this atom, Ian?
Is it hydrogen?
That's right. Ian, not only is this hydrogen, it is a unique form of hydrogen. Do you know the name of the isotope?
I definitely don't know.
Anyone out there in TV land know the name of this famous hydrogen isotope? No? It's called protium. Okay, Ian's passed the test. Let's have one of you others try it. Let's build another atom. Atomic number of 1, mass number of 2, electrically neutral. Nori, can you build that atom for me? You feel like being put on the spot? Embarrassing yourself? Yeah, you do. Come on, be a sport here.
So if A is the atomic number, there's going to be 1 proton.
Correct.
And 2 neutrons? No.
Hold on. The mass number is 2. That means 2 nucleons. Nucleons, are, right?
So 1 neutron.
That's right. Because if you add one neutron,
That would be 2.
you have a total of 2 nucleons, right?
Mm-hmm.
How many electrons will this atom have?
1.
That's right, because it has to balance the number of protons to be neutral. Do you know the name of this atom?
No.
Well, we learned something about the atomic number, didn't we? Does anyone know the name of this atom?
It's still hydrogen.
That's right. That's my point. Because the atomic number defines the atom, this is still hydrogen, but the difference is that this is an isotope of hydrogen. It's not protium. Does anyone know the name of this isotope? It's the most famous isotope in all of nature. It's called deuterium. These are examples of isotopes, and they're kind of famous isotopes. Let me explain why. Suppose we were to go somewhere together, somewhere cool, like in outer space, and we take our spaceship and we fly, I don't know, let's go to the Eagle Nebula, because the Eagle Nebula looks like a pretty cool place to be. Okay, so I take my flying saucer and I travel and head out to the Eagle Nebula, and I start looking around at all this gas and space, and I think, wow, that's pretty cool looking stuff. I wonder what all this beautiful glowing gas is made out of. So what I do is I attach a big cosmic vacuum cleaner, a big shop vac to my spaceship, and I start sucking up gas from the pillars of creation. And as I suck those gas particles up, I start counting the different types of atoms I find. You know what I'm going to find? Basically all of it. Oh, do you know, Ian?
I think so.
What do you think?
I remember stars are pretty much entirely made up of hydrogen and helium. So
that's right.
Fun.
Do you know the ratio of hydrogen to helium?
I do not.
If you are, it's different if you do it by mass than if you do it by atoms, because heliums have 4 times the mass of hydrogen. So let's not do it by mass. Let's do it by number of atoms. As you sucked up that gas, Ian, you would find that for every 10 atoms that you collected, 9 would be hydrogen atoms and 1 would be a helium. So basically 9 out of every 10 atoms is a hydrogen. You might occasionally find a carbon or a nitrogen, but you'd have to suck up thousands before you found one of those. So as Ian said, most of this is hydrogen and helium, and it's 9 parts hydrogen to 1 part helium. Okay, now Ian, here's what I'm going to ask you to do. I'm going to ask you to collect that big box of atoms and just throw all the heliums back out into space. And just let's take a look at those hydrogen atoms that we've collected. If you just counted up all the hydrogen atoms that you got, you would find most of them were protium atoms, but some of them would be deuterium. What would be the ratio? The ratio would be for every 6,000 hydrogens or 6,000 protiums that you collected, you would collect 1 deuterium. This 6,000 to 1 ratio has a special name in science. It's known as the cosmic abundance of deuterium. And what's cool about the cosmic abundance of deuterium is it tells us that all of the shit that we find here on Earth was ultimately once part of those cool gas clouds out in space. For instance, let's take my delicious water, which I just spilled on myself as a part of a dramatic demo. Okay, you guys know that water is a molecule, H2O. Let's just take a peek at that in case you don't know nothing about nothing. We got to fix that, okay? So this is what a water molecule looks like. Slide 23. Now, not all of the water molecules in my glass of water are actually H2O, 2 hydrogens and 1 oxygen. Let's look at a different picture here, okay? If you could count all the water molecules in this glass of water, you would find that 1 out of every 6,000 molecules actually had a deuterium stuck to it instead of a protium atom. So you would call that DHO. And by the way, if you counted 12,000 molecules, you'd actually find something called heavy water, D2O. You can actually isolate all the heavy water molecules from a glass of water, and you can create a substance called heavy water. And heavy water is just like normal water, and it tastes like normal water, but it's like way heavier. And if you drink it, it'll like weigh your belly down more. And people use it in nuclear reactors to absorb neutrons. And I think it doesn't really affect you, except I did read about one study and where they fed a dog 7 liters of heavy water, and then it got sick. Okay. Now, okay, but I think if you fed anyone 7 liters of water, they would probably feel pretty uncomfortable, especially if it was heavy water. I don't know if I agree with the ethics of that experiment. How did they get past the IRB? I don't know. Scientists can be crazy people sometimes. But the question is heavy water different than normal water? Not really, because it's the chemistry, the number of electrons and protons don't really change, but it has a different mass, and it can affect things like nuclear reactions. Delicious light water. I love it. Okay. Do you know that the 6,000 to 1 abundance is present in my water glass? It's present in the Eagle Nebula. It's present in the icy surfaces of comets, kind of, sort of. Scientists actually use slight changes in the ratios of isotopes to investigate the history of where things like water has come from. For instance, we had 2 competing theories about where Earth's water and the oceans came from. One idea was volcanoes spit it out. The other idea was comets collided with Earth in the early solar system. We actually flew a spacecraft to the surface of this comet called 67P Gerasimenko. We took a sample of the ice at the surface, and we could detect microscopic changes in the abundance of deuterium that conclusively proved that comets did not bring water to Earth. So scientists actually use these slight differences in isotopes to tell about the history of where stuff comes from. Very cool business, okay? And they do this across all branches of science: biology, chemistry, geology, whatever, you name it. Okay, let's shift gears for a bit and let's talk about how these little these little factories can create light. So we have to have a discussion about light to get through today's homework. So I'm going to push through a couple of different concepts for you guys. Light is an electromagnetic wave. It's a ripple of electromagnetic energy. And what that means is I used to have this really cool flash animation, and it don't work no more. A friend of mine tried to help me, and he told me about this website where you can run flash demos, but so far I haven't been able to get it to work. I'm going to give it one last shot because this would be really helpful in trying to teach you guys a little bit about light. There's one on a radiating charge, which I really love. And it would, whoa, baby. Come on. Huh. Oh. Let's see if I can do this way. I'm not going to spend more than a second or two on this, but it would, the payoff. Wait, why does it not? This is a flash file, right? Nah, all right. Failed again. Sometimes when people make models of a proton or an electron, they'll represent the essence of charge coming off of them as something called an electric field. You might have seen this before. Now you can ask me, is the electric field real? I would say it's absolutely real. You can't see it, But egads, you can feel it when you pull your socks out of the dryer and they're sticking together, or when you rub a balloon on your hair and you stick it to the wall, or when saran wrap wraps around a banana. Those are all examples of the electric field in action. It's the essence of charginess that surrounds your positive or negative charge. Anytime you grab one of these charges and you give it a little wiggle, you can make ripples in the electric and magnetic field. And it is these ripples or waves in the electric field that constitute light, okay? It's when you take an electric field and you cause it to wiggle and you make a wave. So let's sort of define this. This is just a cartoon here, although I'm kind of pleased with my artistry. Let's define light in the following way. Light is an electromagnetic wave. And that means there are two parts to it. One part is the electric field. The electric field is associated with static charges. Static charges means they don't move, they're fixed in place. And the second part is the magnetic field. The magnetic field is associated with moving charges. When charges start moving around, they generate another type of field called a magnetic field. Let me show you a little model of what we understand light to look like. Excuse me. If I can go forward here. So here's a model of a continuous stream of light. There are two parts. You guys will notice the electric field is a wave in blue. It's an oscillating wave. And the magnetic field is perpendicular. You really need some good 3D art skills to draw light. At the same time there's an oscillating electric field, it also has a magnetic field which oscillates along with it. But the magnetic field and the electric field have a 90-degree angle with respect to each other. And this wave of electric ripple travels through space. Let's show a kinetic example of it here. So these are actually fields here. This is a more sophisticated picture. It's showing the electric field as sort of like these little green arrows, and the magnetic field is little blue arrows. And this wave actually travels and undulates through space. Now, we need to talk about some of the properties that waves have for you to understand light. So let me just freeze on a wave here for a second and let's look at this. Actually, I think if I do my drawing tool, it'll automatically freeze. One of the key properties of waves is called the wavelength, and it's the distance from crest to crest of your electromagnetic wave. It could also be from trough to trough or from node to second node, whatever you'd like. I also want to say something else about light before I go on. The picture of light that you just saw was kind of a continuous stream of light. But light is comprised of little packets. Let's call them packets. I don't want to call them particles. Little packets called, you might have heard of this before, photons. A photon is a packet or like a particle of light. You might imagine drawing it as a wave that's kind of localized in space. It's kind of like a little moving BB wave, okay? And a good analogy is that photons are to light in the same relationship that atoms are to matter. For most of you, you're quite comfortable imagining that matter is made up of these tiny little BBs called atoms. So now I want you to imagine that light is made up of these tiny little BB particles called photons. The truth about photons is they exhibit something called wave-particle duality. And at some point, I want to tell you more about that. It means sometimes they act like particles and sometimes they act like waves. And the truth is they act like both, and you just have to freaking deal with it. All right? Okay, I can do this. I can get to all the stuff we need for our homework. Let me know when you're done copying, Jenna, and I'm going to erase. Can I erase? Everyone cool? All right. Okay. The last little bit that we need to do before we can tackle our homework today, we've almost done everything. We need to talk a little bit about the properties of waves. And these are properties that are common to all waves, but here we're going to be taking a look at photons in particular, okay? Our first property is called wavelength. We're going to use a very specific symbol for that wavelength. It's the Greek letter lambda. Looks kind of like an X that's missing an arm or an upside down Y, however you want to do it. Okay, and wavelength, of course, is the physical distance from crest to crest of your wave. It's actually a distance. So wavelength can be measured typically in units like meters. But in the case of visible light, we tend to use nanometers a lot. A nanometer is defined as a billionth of a meter, and that's going to show up in our homework today. So meters are the standard unit, but these are often more convenient to use nanometers. Another property of light is the frequency of the wave. The frequency of the wave, which we're going to use the symbol a curvy lowercase f, the frequency is defined as the number of cycles per second of a traveling wave as it moves past you. And here to help explain cycles per second, I'm going to look at that animation of the wave, and we're going to try to do something together. We're going to count the frequency of this wave with an arrow. So let's take a reference position. Let's point to this arrow. And we're going to measure the frequency of the wave by counting how many crests go past it, how many waves go past it. We'll start here. So 1001, 1002, 1003, 1004. So approximately, the frequency of this traveling wave is one wave travels by every 4 seconds. And therefore, I would say that the frequency of this wave is one cycle every 4 seconds, or 0.25. But 0.25 what? What should we use as the units of frequency? It turns out that cycles is a conceptual idea, while seconds are a physical measurable unit. So the units of frequency are a bit goofy. They are the per second. A cycle per second is the same thing as 1/seconds. But people don't like to say 1/seconds. That's the kind of thing that makes them nervous. So we've redefined this as a new unit called the Hertz. Hertz stands for cycles per second, or 1/seconds. The last property that waves have is a property that you might already suspect. It's energy. And the energy E is the energy associated with light itself. I've already defined energy, so I'm not going to do that. But I'll tell you that the units are typically joules. But sometimes we like to use a smaller unit of energy for photons known as the electron volt, where 1 electron volt is 1.6 times 10 to the negative 19 joules. Both nanometers, electron volts, wavelength, frequency, and energy are going to be a part of today's homework. So I kind of need to jam it down your throat before we get to the end of class here today. I kind of screwed up by starting a little late today. Okay. The last thing that you need to know is that there are 3 formulas that relate these 3 properties. But I'm going to need to erase the board for those. So make sure you get all this down. Was that 1 second, Jenna? Is that what you were doing? Oh, you're good. Jonathan, Nora, you guys got this? All right. You guys are fast. I like it. Let's write down those 3 formulas because you're going to need them for class today. These formulas don't really have names. They're just formulas associated with photons of light. So I give them these numbers. The first and most basic formula is that the speed of light is the wavelength times the frequency, where c is a constant of nature, 3 times 10 to the 8 meters per second is the speed of light. By the way, this formula actually holds true for other waves like sound and water waves. The speed of sound is equal to the wavelength of sound times its frequency as well. This is kind of a classic physics formula. The second formula defines the energy of a photon. Believe it or not, this formula was discovered by Albert Einstein. The energy of a single photon is another constant of nature known as Planck's constant times its frequency, where h has a constant value of 7 times 10 to the negative 34 joule seconds. And this constant is known as Planck's constant after the quantum physicist Max Planck. Planck's constant tends to show up anytime you deal with atoms in the microscopic tiny world of photons and things like that. There's also a third formula that is kind of a combination of these two. It comes in handy a lot. So let's write this down. We can also write the energy of the photon in the following way. Planck's constant times the speed of light divided by the wavelength.
I had a quick question.
Yeah.
Usually when you'd write like say meters per second, you'd write it like over like a bar, but you did times.
Yeah, that's just the brutal nature of units, Nori. Up to now, you're used to seeing meters per second squared. Sometimes, Nori, units aren't divided by. Sometimes units are times by. And
okay.
I'm glad that you're pointing it out because it makes a really big deal. Joules times second is not the same as joules per second. If you really want to go there, Nori, remember that a joule is a kilogram meter squared per second squared. That means that a joule times a second, if you multiply this by a second, is a kilogram meter squared per second. Believe it or not, that has the units of angular momentum. Now, I ask you, would you rather write kilogram meter squares per second, or would you rather write joules times second? Most people would rather write joules times seconds. Either way you cut it, it's kind of a fucking mess. And that's because Planck's constant is kind of a crazy thing. It's a quantum increment of spin, but I can't tell you about that because that's over your pay grade, okay? All right. Now, one of the first people, and this will be kind of like a fun note on which to end our lecture today, just a little demo. One of the first people to investigate the nature of light was actually Isaac Newton. And he did kind of a legendarily important experiment. He created the first spectrum of light by shining a beam of white light through a prism. Now, I'm going to attempt to do this demo, and I warn you, I'm probably going to fail because this demo never really goes off that well. But in class, I used to be able to do it so well because I had a 400-watt projector, and I got really good at creating a prism really fast. But it's still worth it if you guys can just suffer through me fumbling around for a second. I want to plug this in, and I want to attempt, I'll turn the lights down. I'm going to need a, hold on a second. I just need to get my extension cord here. Oh, play some funny games. right, here we go. I got a plan. I got a plan for this today. I'm going to turn the lights down in my apartment. It's actually pretty effing bright in here, so I can't. Okay, let's see if I can do what Isaac Newton did, and let's see if I can make a spectrum by taking white light and passing it through a prism. Oh, here we go. It's not as bright as I would like it. I almost got this. I'm trying to see what you guys can see on the board. I've just about.
Yeah, I was able to see it for a little bit.
You have to have the light really directional. I'm trying to use a spotlight here. Could you see the rainbow for a second? I can see it on my board, but it's faint. So I know.
Yeah, I definitely saw it for a little bit. It's just it keeps trying to focus on like the brighter light, so it.
Oh
it's
yeah,
like,
you know what? I bet. Let me see if I can do something. One last thing. Let me turn off the auto. I can't. Can I do auto wipe? Everything looks fucking crazy. I wonder if this would work though. Oh, I've just about got it right near the E of the photon. It's just so stupid faint. Your beam of light needs to be collimated into a slit, but every time I tried taking like a cardboard box and cutting a slot in it, it just didn't work that well. I should experiment more with it, but I tend to not think about it until I'm here in class with you guys. I'll try one more. For some reason, I was so damn good at this at CCRI when I had that. This is probably like 120 watts or something. That thing was 400 watts. So it was so bright that you could just make really, really cool rainbows with it. Oh, here we go. Booyah. Can you see that? You can. It's right above Planck's constant. Can you see that rainbow?
Yeah.
That's actually the best I've gotten. Let me try one more experiment. You guys are an experiment in itself. Let me fix the auto white balance again. Okay, let's see if I can do that one more time. That was pretty damn good. Can you see that rainbow there?
It's definitely better than the last one. Yeah.
Yeah. It took me a minute to figure out the angle here. The order of the colors goes violet, blue. Actually, in Isaac Newton's day, they didn't use light blue and dark blue. There was dark blue is called indigo, and I have a personal crusade to bring back the color indigo. Let me show you this in a better illustration, okay? It depends which order you twist your prism. Oh, sorry. Here. So, we're sorry. Here we go. So here's a model of how the experiment works. In order to do it right, not like the piece of shit that I just did for you guys, you really need to collimate the beam of white light into a pencil-thin beam. The reason mine wasn't working well is because the white light was striking the glass at all these different angles. But if you collimate it into a very focused unidirectional beam, when it hits the glass, it will disperse the white light into basically a rainbow, which is a whole bunch of different wavelengths. That's what you're measuring when you measure wavelength, is essentially color. Now, the order of the rainbow always has the same colors. Violet, in Newton's day, they called this color indigo, kind of dark blue. Blue in Newton's day was exclusively reserved for sky blue or cyan. So violet, indigo blue, green, yellow, orange, red. Now, I have memorized this as VIBGYOR, but other scientists who twist the prism in the other direction, they oftentimes like to put red on the left, and then the acronym becomes Roy G. Biv. If you talk to a scientist and you say Roy G. Biv, they know exactly what you're talking about. The only thing is, I like to do VIBGYOR because I like to have the shorter wavelengths. Purple is 400 nanometer wavelength on the left, and red is 700 nanometer wavelength. I like to have that on the right. This is what is known as the visible continuous spectrum, and you're going to learn more about it next week. The colors are pegged to wavelengths of light. And next week, we'll actually do a pretty cool lab on spectroscopy.
Question about that. By next week, do you mean after spring break or?
Oh, right. Whoa. Cancun. Not. Okay. So anyways, I guess, I don't know. I might go to I actually might go. I usually don't go anywhere in spring break, but I might go to New York this spring break. I'm excited. But for the most part, yes, I mean after spring break. I forgot about that. Okay, let's just hack our way through the rest of the homework because I've kind of used up my time for the day. I hope you guys do have a good spring break, and yes, we'll have to get back to that a week later when I'm sure we'll all be out of sorts. Should we take our little 15-minute break before we tackle today's homework? Today's homework is not as hard as the last two that you've done, so, or those two nasty ones. Today's homework is a little more straightforward. I'll take a 15-minute break. iPhone time is 1:40, so at 1:55, we'll get to it. Sound like a plan? All right, I'll see you guys then. Let's do this like Judas. I have a friend who's coming to have a study session with me today after, as I furiously compute your grades. So if my phone rings, I just need to buzz her up here, and then I can get right back to business. Don't get too distracted. Are you guys ready to go? Do you have the homework numbers?
Yeah.
Let's do our usual thing. Let's put the name down. Astronomy 1010 with your section, whatever that is. Okay. Let me just get my camera angle under control here. Wait, hold on. Okay. You guys can read that okay, right? Looks good? Thanks for all the feedback. Okay, so this is homework number 5. Chapter 5. And what are the numbers, Ian?
44, 53, 54, 55, 57.
7?
7, yeah, 57.
All right. Is this volume all the way up? Hold on. Function. Yeah, all right. Okay, so Ian, take us out with chapter 5, number 44. What's the title?
1 second. 44 is.
If you guys could all call up the questions, that'll smooth this whole operation out.
44 is Atomic Terminology Practice 2. And here's what it says. There's part A, B, and C. A says, what are the atomic number and atomic mass number of a fluorine atom with 9 protons and 10 neutrons? If we could add a proton to this.
Is that, is that all part of part A?
Yeah, this is all part A.
Oh, okay. So could you read the whole thing again? Sorry.
Yeah, that's fine. Okay, part A. What are the atomic number and atomic mass number of a fluorine atom with 9 protons and 10 neutrons? And then this is still part A. If we could add a proton to this fluorine nucleus, would the result still be fluorine? Still part A. What if we added a neutron to the fluorine nucleus? Explain.
Wow. My spelling sucks. All right. Did I get all this right?
Yeah, looks like it. And then explain at the bottom, but yeah.
We'll skip the explain part for once. Let's see if we can do all this. Okay, who wants to get a whack at this? I felt like today's lecture on the atoms was really straightforward. To me, I understand this stuff, right? I've been thinking about it longer than you guys have, presumably. So why don't you guys try to flex your muscles here and see what you can do. What's the atomic number?
19.
Would be-
Remember, Jenna, the atomic number is just the number of protons.
Okay. 9 then.
And in that case, what would the mass number be, Jenna?
The mass would be 19.
Yeah, the mass number would be 19. When I think of mass, I think of kilograms. I'm just going to be a bit technical there. Okay, if I add a proton, will it still be fluorine? Anyone know what the atom is whose atomic number is 10?
I don't, but it wouldn't be fluorine.
It wouldn't be fluorine.
Yeah.
It turns out that that's neon. No. It would become neon. Atomic number 10. How about if I add a neutron?
I think it could say the same. It would be an isotope, right?
Yes. Yes. Still fluorine. But a new isotope. And the way we would write that is we would write it as fluorine 20. And I believe you put the mass number up to the left is the traditional method. So this is fluorine 19, but the new isotope would be fluorine 20. That's standard notation there. Okay, how about B?
All right. Part B says the most common isotope of gold has atomic number 79 and atomic mass number 197. How many
Sorry,
protons?
190 what?
197, sorry.
7.
7, yes.
All right.
And then it says, how many protons and neutrons does the gold nucleus contain? If the isotope is electrically neutral, how many electrons does it have? And if it is triply ionized, how many electrons does it have?
All right. This should be straightforward. Number of protons in gold. How about Ryan?
79.
Oh, sure. Anyone? No, Ian.
Sorry, I was just still writing stuff down. That's why I didn't answer immediately. But yeah, 79.
Sorry. What did you say?
79.
Excellent, because that's just the atomic number. Number of neutrons?
$118, if my math is right.
Okay, can someone else verify that? Thanks, guys.
I got 118 too.
Okay. How about if it's electrically neutral? How many electrons does it have?
79.
Yeah, the same number. That's pretty straightforward. How about if it's triply ionized? You know what that means, right?
I'm going to want to look at my notes for that, but maybe.
Technically, that's an ambiguous question, but I think you'll know what to do.
So it's what I wrote down is that it's an atom that has
I'm sorry, Ian?
removed or multiple removed electrons.
Yeah, usually when they say ionized, they talk about ripping the electrons off.
hmm
So let's assume they're taking the electrons away.
So when they say triply, did they literally just mean like 3?
Yeah.
Okay, I wasn't sure if it was like triple of something. Okay, so then that would just be 76.
That's right. You guys are doing good with this stuff. I think it's pretty basic stuff, but it's still good to review it. You can screw up.
Wouldn't triple be like times, not necessarily times or anything, but just
They don't mean triply. They don't mean triple in the time sense. The way each scientific discipline, like chemistry, they have their own kind of vocabulary. So from what I remember from my chemistry class, they would say singly ionized, and that would mean remove 1 electron. Doubly ionized, that would mean remove 2 electrons. Triply ionized. So not so much times, but it doesn't quite gel with like mathematical terms. It's chemistry specific. So I could totally get that being confusing, but you just kind of learn this, the code, the language code of chemistry, and that starts to make sense.
would you add it because you said that sometimes you do add it, or would that?
Yeah, that's what's kind of, if you have to be very technical about these questions. The answer to this could easily be, and if you guys were doing this without me, which would be suicide, I would accept 83 electrons as also an acceptable answer because that's triply ionized. Ionized can go either direction. But more often than not, when you're focusing on a problem, you're focusing on atoms which are losing electrons. Okay, I'm going to erase part A so that I have room for part C. There is a part C, correct, Ian?
There is, yes.
And what's that puppy, ask us?
All right. Part C says uranium has atomic number 92. Its most common isotope is 238U, but the form used in nuclear bombs and nuclear power plants is 235U. How many neutrons are in each of the 2 isotopes?
Okay, so the way we would write these 2 isotopes, once again, is to put the mass number in the upper left corner, 238U, 235U. So we want to find the number of neutrons in each. How am I going to do that?
Well, since we know that there are 92 protons and I think 238 is the nucleons, right?
So we
You
just
would subtract.
238 minus 92. So 146 for U238. And how about U235?
143.
Pardon me, one more time?
143.
Yeah. In fact, it is the fewer number of neutrons which makes this uranium nucleus so unstable. So you guys are going to learn a little bit of pigeon nuclear reactions. I actually really enjoy teaching that stuff to you guys. When we study the sun, I guess a week after spring break, we're really getting behind here. But neutrons, the job of a neutron is to be a kind of nuclear glue. It's to be, oh gosh, I still have these all backwards. I'm going to delete this. Boom. Okay. The job of a neutron is to be a kind of nuclear glue for atoms. So normally the reason you need neutrons is when you've got a big fat nucleus like uranium, that's 92 protons that are all smushed together. And they're all trying to push each other apart according to the rules of electromagnetism. The neutrons kind of glue this nucleus together and make it stable. But if you shave off a few neutrons, if there's isotopes that have fewer than the average number of neutrons, all it takes is some little destabilizing factor, like a high-speed neutron hitting this thing, and whack, the whole damn nucleus will split apart into radioactive cesium and rubidium and release a crap load of energy in the form of gamma rays. So isotopes that have fewer numbers of neutrons tend to be unstable and they become radioactive. All right, that's good for part 1. Let's queue ourselves up for question 2. Has everyone got this? I'm erasing now.
I have a question.
Yes.
It's not really about this, but I have a
Anything else?
tendency to forget things, so I'm just gonna ask it now.
Okay.
I went over on my grades, like on Blackboard, and I noticed that I'm not sure how Blackboard like calculates like the homework grades or like the lab grades, but right now it's like obviously like in the red because it's out of like 222 and like.
Yeah, you don't want to. Blackboard has these columns called total, which they will not let me get rid of. That is not how. That's not how that works, right?
My question was how many points were the homework out of, because it only says I got 75, and if we did 4 that means that I missed one, but I submitted all of them.
Okay, that is disturbing. I'll take a peek at you right now here, Nori Murad.
That's what was concerning to me, because like I didn't really care if it was red. I know how I kind of figured out how it worked, but if it was 75, that means I missed one, and I'm pretty sure I did all of them.
Well, guys, this is what I'm trying to warn you about, is that some of you think you've submitted everything, but little weird things happen. And I'm willing to believe you, Nori, but what we need to do is figure out what happened. So because this will be of interest as a general question to others as well, if you guys don't mind me just kind of calling this up here, just so I can see it'll help you get a better sense of how the grading is done here. I keep track of everything here inside my Excel sheet. So I'm going to divide, so each homework is out of 25 points. So you should have 100 points if you've turned everything in. And where are you? Yeah, I'm seeing a 0 for your homework number 3. And if you say you turn that in, well, that's troubling. We got to figure it out. For instance,
that's the one that I had submit with you that one time.
Oh, you had to submit it over email?
No. I think I accidentally submit one, like 3 and 2, I think it was. And
wait, what the hell are you talking about? I'm totally lost.
So
keep in mind, Nori, I have hundreds of students, so.
Homework 3, I had submit in section 2 or slot 2. So
You
then
mean homework-
I resubmitted
wait,
all of those.
You submitted homework 3 as homework number 2? See, this is the kind of shit that sucks.
No, we fixed it.
So is it in there and I just haven't updated my grade book?
I guess. I'm not sure. I can't see it off my end because the slot is closed, but I'm pretty sure that we fixed that.
Well, you can see it. What you guys can do is you should be able to go. See, I have a needs grading, and then I have a full grade center where I can see everything, right? So if you say we submitted it, then I don't see why it would have. Let's just go to you here. This is what I have to do. I have to go to the full grade center. I have to look up your last name. Look at all these people. Look at all these humans I got to keep track of. It's insane. Okay, so now you're second from the bottom here, right? And this thing is awful to use. I have a 0 for homework 3 for you. I don't have anything there, so we got to figure that out. Do you have a copy of it in your notes so I can believe you?
I do.
All right.
Do you want me to show it to you now? Or?
Well, why don't we deal with this after class? But you say we already did this, but it just didn't show up? That's scary. All right, hopefully not too many other people have this issue, but okay, so Nori, what you're going to do is you're going to hang out after class and we'll straighten this thing out. Sound like a plan?
I do have somewhere to be at 3:30, but
Here we go. Here we go. Look, how may I serve you? Welcome to McDonald's.
I can
I take your order?
It's okay.
All right, so then go do your thing and talk to. Well, I got to compute midterm grades today. How important is it?
It's okay. It's therapy, but it's okay.
You know what's good therapy? Getting a 100 points on your test. That tends to make you feel pretty good, right? Or getting 100 points in your homework grade. I'd say that's the most important therapy. I don't want you to miss your psych appointment.
It's okay. I'm good. No.
All right, so
not
we can
yet.
hang afterwards?
Yeah,
All
as
right.
long as it's not like too late.
All right, well, let's move fast then. Why don't you read the next question since you're on a crunch? Chapter 553.
Okay, so all set?
Yep.
Electric bill. Your electric utility bill probably shows your energy use for the month in units of kilowatt hours. A kilowatt hour is defined as the energy use in 1 hour at a rate of 1 kilowatt, which is 1,000 watts. That is 1 kilowatt hour is 1 kilowatt times 1 hour. Use this fact to convert 1 kilowatt hour into joules. If your bill says you use 900 kilowatt hours, how much energy did you use in joules?
This is a perfect question for you to read, Nori, because you asked me a cool question today about Planck's constant. And you said, hey, the gist of it was, Brendan, I'm used to seeing units as meters per second. I want to say something per something because it sounds good. But in fact, units can also be multiplied. And in fact, people often incorrectly state that their electric bill is measured in kilowatts per hour. In fact, it's not true. An electric bill is measured in kilowatts times hours. And believe it or not, a kilowatt times an hour is a form of energy. Okay, here's something I was supposed to explain today in class, but I didn't because I was running out of time. There is a concept in physics called power. And power is energy per unit time. You can think of power as a rate of energy flow. That's what it is. In the same way that you would never confuse meters per second with meters, a speed is something that you travel at in your car, whereas a meter is a length, and they're totally not the same thing. The same is true for power and energy. Energy is one thing. It's what we talked about last class. But power is a rate of energy flowing through a system. You could talk about the power of a light bulb shooting off light. You could talk about the power of a hairdryer or an electric guitar amplifier. Power has its own units. The units are joules per second, because those are MKS units of energy and time. And what we do is we redefine joules per second as a watt. A watt is defined as a joules per second. You'll notice that for kilowatt hours, the reason why kilowatt hours are the same as energy is because kilowatts multiplied by a time brings you back to energy. The difference is the units are all effed up because we're not just using watts, we're using kilowatts. And we're not using seconds, we're using hours when we bill you when National Grid bills you. I don't want to put a we in there because those bastards, well, we got some score to settle. Okay, anyways. What's up with this monopoly on energy? Anyways, okay. So why don't we try to figure out, there's two goals to this problem, and I'm sorry, I might have buried it in my description here. Our two goals are first to take 1 kilowatt hour and to convert that to some number of joules. And then they tell us that a typical bill for your electricity might be 900 kilowatt hours. And then we want to convert that to joules too. So we actually have two jobs to do here. I bet you'll never guess the technique that we're going to use to solve this problem. I bet it would never cross your mind what the perfect skill set to solve a problem like this is. Right?
Now I wouldn't
No
be
clue.
able to guess.
Say that?
Now that you've said that, I won't be able to guess it.
Oh, really?
No clue what you mean.
Is it a conversion factor?
Fuck yeah, it is. This is a conversion problem. You got units jiggling around with units. You got watts and kilowatts. You got seconds and hours. This is a job for, take it away, Ian.
Unit conversion.
What's that called? That skill, that special skill.
Or
I forget the name.
It's the whole
dimensional analysis.
dimensional analysis. Say it loud, say it proud. That's the whole point of this stupid class, in some ways, is dimensional analysis. Ian, atone for your sins, okay? Ian,
Okay.
do you guys have this? Because I'm going to erase so I don't have to move my board here. Okay. Here's what you know, Ian. You know that 1 watt is 1 joule per second. You know that 1 kilowatt is 1,000 watts. Use dimensional analysis and help me convert 1 kilowatt times hour, into joules.
Okay.
What's step 1?
So here's what I'm thinking. We're gonna have to convert the kilowatt and the hour separately.
Yes,
Right?
that's
Because
correct.
it counts the joules over seconds.
I'm sorry, say that again. You're a little quiet today. I think you might be far from your microphone or something.
Yeah, a little bit. Sorry.
Right.
So we would want to do the kilowatt first into watts, I'm guessing. So
all I want you to do, bro, is to use the 4 steps of dimensional.
all right.
I want you to do it. You multiply by division.
One kilowatt times the division bar.
Good.
And then
kilowatt hour times the division bar. We're going to work.
We have to do it together.
Well, yes, we have to keep these units together, but we can deal with each one separate on a separate division bar.
Sure.
But we are dealing with a unit of energy called the kilowatt hour, the kilowatt times hour. So we have to start with both. All right.
Okay. Kilowatt unit on the bottom of the division bar, and then watt on the top.
Nice.
And then you would
We
put
can put the numbers
on top and then 1 on the bottom.
Nice. Okay, what you have successfully done is, well, actually, let me ask you, what are the new units that you have here once you've canceled out kilowatt hours?
We have watt hours.
Very good. You now have watt hours. A watt times an hour. You could also say hour watts, but that doesn't sound as cool. You're dealing now with watt hours. What am I going to do?
Well, you said we have to do them together. So would you then multiply again by a division bar and then put hour on the bottom? And then I don't remember off the top of my head the conversion to seconds. That's 3,600. Is it?
True.
Okay.
For the benefit of other people who don't do that math in their head, why don't we do minutes and then seconds? Because everybody knows that, right?
Okay, sure. And then minutes on top. And you would do 60 for minutes and 1 for hour. And
now
then
this cancels out our hours.
Yeah.
Now we're dealing with watt minutes.
And then you would do same thing, minutes on the bottom, seconds on top, 60 and 1.
Okay. Why don't you go ahead and punch that up for me, class?
I got 3,600,000.
Put it in scientific notation.
Sure, yeah, that should have been done. Okay, 3.6 times 10 to the 6th.
Now, let's look at our units here. What are the units that we currently have?
Watt seconds.
But we were supposed to convert to joules.
Would we? Well, okay, so because we have written 1 watt is equal to 1 joule per second. So you could turn that into 3.6 times 10 to the 6th J times S over S.
Right,
Okay.
which is what?
Joules.
That's right. Watt seconds are the same as joules because a watt is a joule per second. So I was just making sure that you guys followed that very last step, and you did that, Ian, beautifully.
Thanks.
Okay, what's our next job? Our next job is to convert 900 kilowatt hours. Ian's off the hook now, but Kim, maybe you'd like to help. If you're down.
No, I'm here. Sorry.
Okay.
Okay. So we're going to start with 9,000 kilowatts hour times division bar.
Okay.
It's going to be kilowatts on the bottom and watts on the top. Should be 1,000.
Hold on, Kim. Slow down for a second. I want to show you and everyone else a trick. We
Okay.
don't have to reinvent the horse, okay? See, Ian went to the trouble of breaking down the watts, the kilowatts, the minutes, the hours, and the seconds. And in a way, Ian has helped us derive a new conversion factor, which is 1 kilowatt hour is equal to 3.6 million joules. My suggestion, Kim, is whereas before we treated the kilowatt and the hour separate, as a demonstration, now we can treat them as a single unit because we have a single conversion. Does that make any sense, what I just said?
Yeah.
So what units would I want to put top and bottom?
So we're going to put 3.6.
No. You don't get to give me numbers until your units are in place.
Sorry. Kilowatts. Well, it'll be joules on the bottom. An hour on the top.
I don't think that's going to work because now you have a kilowatt hour squared per joule and things just got a lot worse.
Okay.
So that didn't work. Remember, one trick that Ian's always using is he always makes sure that whatever unit on top is matching the unit on bottom. That was part of his success there.
So it'll be kilowatts per hour on the bottom.
Wait, did you say per hour?
I said times.
If you say kilowatts per hour,
Yeah.
that's not okay for me because
No, it's
that means
times.
a kilowatt divided by hour. Do you want to know what that is? Kilowatts cancel with kilowatts, and now you have hours squared. I don't think that's what you meant to say. You didn't mean to say kilowatts per hour. You meant to say
Times. Kilowatts times hour.
Kilowatts times hours. And if the times is too awkward, you can just say kilowatt hours. That I'm okay with. And what unit goes on top?
Joules.
Very good. And now you can put the numbers in.
So it would the bottom would be 3.6 times 10 to the 6.
No. You're giving me the willies.
Oh,
Look.
I'm sorry. That's supposed to be on top.
Yes, you've got to keep the number with its unit, right?
And 1 on the bottom. Sorry.
That's all right. Those things happen. I suspect they happen to a lot of you during your test when suddenly you were playing without the training wheels. Suddenly it's a bit harder then, ain't it? Okay, well, so be, you know, I had this friend once, she says she doesn't know how to ride a bike because her parents gave her the bike with training wheels and they left her in the parking lot by herself. And she just leaned over to one side and she biked around in a circle for hours. And so she said, I never learned to ride a bike because I just went around in circles with the training wheels. We occasionally have to have a test to remind you that, you know, the importance of balance. Anyways, could you guys punch that up for me? Jenna, since it's a big number, why don't you just slap it right into scientific notation and tell me what the answer
Yep,
is?
I got 3.24 times 10 to the 9th joules.
I like it. $3 billion joules. That's a lot of joules if you pay for that thing. You know what's funny about getting energy from Mr. Power Plant? Electricity is just pushing electrons. So you're really just renting a flow of electrons. First, the little electrons come out of this spike and they go through your iPhone, and then they go back into this spike and you send them back to National Grid. You're essentially renting the flow of electrons through your iPhone, and you give the electrons back. What do you get to keep? You get to keep the energy. All right, that's the answer to 53. 2 down, 3 to go. Nori's got an appointment. I'm erasing. Okay, what's the title?
I can read it. It's radio station.
Thanks. Okay.
What is the wavelength of a radio photon from an AM radio station that broadcasts at 1,120 kilohertz. What is its energy?
Okay, once again, we've got two jobs to do. This is going to be the first time that you guys dealt with a photon-like problem. Let's draw a picture so that you get an understanding of what's going on. If you want to build a radio tower, you just take like a wire and you put it on some support structures, and then you put a little red blinky light on it so that airplanes don't bump into it. And you cycle some electrons up and down. Boy, that's a crappy looking radio tower. Let's see if we can improve on that. I think my radio tower should look like this. Okay, there we go. Okay, that looks more like a radio tower now. Let's put the blinky light on top. And we take electrons and we cycle electrons up and down the pole. We're going to cycle them at 1120 kilohertz. And as we cycle the electrons up and down the pole, a big ass, long ass radio wave is going to come out and transmit some Stone Temple Pilots to your local radio boombox. Okay. Obviously, the 1120 kilohertz is a frequency. Our job is to find the wavelength. I wonder what formula we could use to do that.
The first of the three formulas.
Excellent. And that formula is speed of light is wavelength times frequency. Up to now, I've been doing most of the algebra for you, but it'd be kind of fun to see if any of you have the chops to solve this for wavelength. Anyone think they can handle that? Jenna.
Actually, yeah, I could do it. I could do it.
All right.
Okay.
Now we had a lesson once about not about left or right, but top or bottom. Remember that discussion?
Mm-hmm.
Okay.
Well, I was going to start by just plugging in everything that we do know, so we know.
Oh,
like
no. That's amateur hour 101
Oh, okay.
there. You never, ever do that. That's just slovenly in terms of good style. You solve the equation in terms of variables. You put numbers in at the end. In other words, Jenna, I want to know that wavelength is equal to what?
F times C.
Oh,
C over F.
That's right. C is on the top. We take the F and we push it down to the bottom. All right. Now, C is the speed of light. Today in class, I told you that was 3 times 10 to the 8 meters per second. Our frequency is 1120 kilohertz. This don't look good to me. It doesn't look like meters per second and kilohertz are going to cancel. What am I going to have to do then? Ryan, did you have a thought?
Are we gonna have to use dimensional analysis to convert one to the other?
Yeah, what do you want to convert kilohertz into, though? That's basically what I'm asking. I want to see if you understand what that's supposed to get turned into.
Into seconds?
Not into seconds, because seconds are not a unit of frequency. That's not the way we say that, Nori.
Just into hertz.
Into
No.
hertz. And hertz is a per second. Nori, I want to be real clear about this. Seconds on the top is not the same thing as seconds on the bottom. Seconds on top is seconds. Seconds on bottom is per seconds. Okay, so 1120 kilohertz. Nori, what am I going to do? You're going to do step 2 of dimensional analysis, which is?
Divide by division bar.
Yep, multiply by a division bar. Okay. Now give me some units, bottom and top.
Would it be, what is that, kilohertz
Yep,
in the bottom?
yep.
And I'm not really sure what's going to be on the top.
Hertz on top.
Hertz on top. We got to deal with the kilo part first. Now, I never told you the conversion from kilohertz to hertz.
Is it 1001?
Yeah, duh. I wanted you guys to know that kilo always means 1,000. Thank you, Jenna. Thank you for understanding the metric system. Anytime you see kilo, first lecture, kilo is 1,000. Okay, so how many hertz does that give me? Then, Jenna, anyone? Jenna, I bet you could do that in your head, couldn't you? Don't punch it in your
Yeah.
calculator like a goofball. Just look at it.
Sorry, 1.12 times 10 to the 6th.
Excellent. Now, that's 1.12 million hertz. But remember, in today's class, we learned that that's also the same as 1.12 million cycles per second, or per seconds. And that's what I'm going to put in to my equation, because now I can balance my units properly. Punch them up. You can keep 3 sig figs if you'd like. The speed of light is actually good to 3 significant figures as 3.
I just want to mention too, you forgot to put to the 8th with the speed of light, 10 to the 8th.
Oh, wow. Jesus, thank you. Now that is last night's scotch talking right there, okay?
Yeah, I was wondering. I was like, am I missing something?
Thank you. No, I was testing you, and you passed the test. Congratulations. Okay. Okay, guys, any day now.
I got 268.
And the units?
Hertz.
False.
No?
Do your unit balancing.
Is it meters?
It's just meters. That's right, because per seconds cancels with per seconds. Guys, this is a single radio photon. I don't think you guys are really appreciating what that means. We tend to think of light as being made up of short wavelengths, particles, because visible light is in the nanometer range. But radio photons have lengths of 268 meters. What else can you think of that's 268 meters long? Well, shit. A blue whale. The average length of a sexually mature female. Are the males longer? Oh man, a blue whale is 33 meters. So that's certainly not long enough. You'd have to have like 20 blue whales. What about, how long is a football field? I have no idea. Any sports shit. How long length? It's like 300 feet or something. 100 yards. 50 meters. So literally this thing is like 5 football fields long, a single radio photon. Radio waves are huge. Their long wavelength is one of the reasons why they can pass through buildings and people as if they were transparent glass. Did you know that your cell phones, they don't operate quite at the AM range. They're a little bit shorter wavelength. They're probably in the centimeter to meter range. But these things are radio transmitters as well. Okay, I digress. What are we going to use to find the energy?
For energy, we do E equals H times F.
Love it. And we've already converted our F into MKS units. So we'll just speed things up. 7 times 10 to the minus 34. The units are joules times seconds. Multiplied by 1.12 million hertz, or per seconds. And what's that give us?
7.84 times 10 to the negative 28th.
I'll let you keep 7.8.
Okay.
Planck's constant is actually 6.63, so I've grossly rounded that. What are your final units?
Joules.
That's right, it's energy. Radio photons are long wavelength, but they are very, very low energy, like low energy Jeb Bush photons, okay? All right, 3 down, 2 to go. We're making progress. I'm ready to erase if you're ready. Anyone copying still, or? Ryan, you down to read?
Yep.
All right. Chapter 5, 55.
55. UV photon. What is the energy in joules of an ultraviolet photon with a wavelength of 120 nanometers or
Correct. Nanometers.
nanometers? What is its frequency?
Okay, so we want to find the energy. We want to find the frequency. And we will draw a model of our microscopic little UV photon. There it is. Okay. What should I do? What should my first step be?
Well, my first thought is that we might have to convert the nanometers to something else.
To MKS units, right? Now you're starting to think smart. Now you're starting to do the conversion before we look for the formula. I like it. So Jenna, since you're so good, why don't you help me convert the wavelength to MKS units? How am I going to do that?
Okay, we write 120 nanometers because that's what we're converting.
Yep.
And we multiply by division bar.
Yep.
We put NM nanometers on the bottom
Yep.
and meters on top.
I like your style.
This conversion factor, do we know it?
I gave it to you in today's lecture. I gave it to you in other lectures as well. It's also in your formula sheet. Why don't you look in today's lecture? It's back there just on the last page of notes.
I have it already if you want.
Oh, Ian, hit us then. Fine. Collaborate.
1 nanometer is 1 times 10 to the negative 9th meters.
I meant to have you guys place it, but let's presume you do it. Now look, you could punch this into your calculator and get 1.2 times 10 to the negative 7, but that's lame. Can I show you a better way to do it? Let's just write 120 times 1, and that's 120 times 10 to the minus 9 meters. I actually prefer to write it this way. It's a little goofy, but let's just think about what we're doing here. We are reminding ourselves that 10 to the minus 9 is the same thing as nano. So when you get real good, you can just swap out nano and replace it with 10 to the minus 9. I actually read this in my head as 120 nanometers. Okay, what formula do we want to get the, let's do frequency first.
C equals wavelength times frequency.
Okay. Jenna, since we're in a time crunch, why don't you solve us for frequency since you're getting pretty good at that?
Yep, its frequency equals C over wavelength.
Good.
Oh, man.
Put the wavelength on the other side. We know that the C is 3 times 10 to the power of 8 meters per second. We know that our wavelength is 120 nanometers. Punch them up. Just tell me what you get, Jenna.
Okay, I got 2.5 times 10 to the 15th And that'll be seconds.
No.
Oh, meters squared over second.
No.
Oh, joules,
No.
meters.
No.
Oh, okay, I give up.
Anyone?
Would we wouldn't put it in nanometers, right? Because that's gone.
None of you, you're all talking garbage here. Look, I taught you guys a lesson. A divided by B, C divided by C. What's that equal to?
Is it meters over meters per second?
This truly exemplifies the saying that 3 out of 2 people are bad at fractions. Okay? Y'all be bad at fractions. We gotta
Meters
fix.
squared over seconds.
All right, you're not ready yet. Okay? What does this equal? This is the top of the top, the bottom of the top, the top of the bottom, and the bottom of the bottom. How do I reduce that to a single fraction? I taught you this. You're supposed to know things.
Would it be AD over CB?
That's right. Okay, let's talk about our first meter. What letter does that correspond to?
A.
All right, so that ends up on the top. How about the S? What letter does that correspond to?
B.
B. So that ends up on the bottom. How about this meter? What letter does that correspond to?
That is C.
That's C. And that means it ends up
On the bottom.
on the bottom. Now cancel out common terms. And what do you have left?
Seconds.
No, you guys
One-
don't get
one
it.
over
Right.
One
Cycles.
over seconds.
It's
One
cycles
over
per second.
seconds
Which is a hertz.
Which
It's a
is
hertz.
hertz. That's right. Now you're talking. I understand what you guys are doing. You're saying the only little letter I see there is S, therefore it must be seconds. False. It matters that's in the denominator. You got to pay attention to that stuff. And right, that means hertz. It's cycles per second. Okay. So these are painful growing pains that you guys are learning. I feel good about this. That's our frequency. Now let's try to work with the energy. Can I erase this? So I don't have to squish? Okay. You guys got all that, I hope. All right.
So painful, I'll never forget.
I'm sorry, Ian?
I was just joking. I said that was so painful, I'll never forget it.
I hope so. I hope so. That's the idea. The idea is to make it. You know what Nietzsche says? He says that pain always brings about questions of origin, whereas pleasure is just content to stop right there. That's why we frequently don't learn things through pleasure. We learn them through pain. Energy. Which formula do you prefer?
Maybe the H times C over wavelength.
Yeah, I like that one for 2 reasons. We have the frequency, so we could use H times F, but you haven't tried the third one yet. And also, it's kind of nice to go from your original given to the answer when possible. So we're going to use the energy of a photon is Planck's constant times the speed of light divided by the wavelength. Planck's constant is 7 times 10 to the minus 34 joules times seconds. The speed of light is 3 times 10 to the 8 meters per second. And the wavelength is 120 billionths of a meter. Punch them up, do your unit balance, and tell me what you get.
$1.75 to the times 10 to the negative 18. power?
Negative 18th? Just
Negative 18?
I got that too.
okay. I'm rounding it to 1.8 because I don't think 3 sig figs is good here. So negative 18th, and what are your units?
Joules?
That's right. Meters cross with meters, seconds of seconds. It's an energy after all, so its units should be joules. Good. Okay, we're doing okay in time. Almost at 3, but not quite. I'm ready to erase if you are. Whew. I think I'm allergic to math. Sorry. 57. Who has everyone read? I'm losing people here. All right, Nori, since you got the appointment, we'll have you read.
Good.
I'm ready.
How many photons? Suppose that all the energy from a 100-watt light bulb came in from photons with wavelength 600 nm. No, in reality, light bulbs distribute energy over many wavelengths. See exercise 51. Calculate the energy. This is A, by the way.
Yeah.
Calculate the energy of a single photon with wavelength 600 nm. B is how many 600 nm photons would have to be emitted each second to account for all the light from this.
Nori, I'm going to pause you right there. This question is this is the one big question we have today. Let's just deal one part at a time. First thing I'd like to ask is I'd like to show you guys my Roy G. Biv or my Vib G. Yor spectrum. What color is 600 nanometer light?
Orange.
Yeah, it's a very pure orange. So in a way, this problem is kind of like if you've ever seen one of those Home Depot party light bulbs where you can like get light bulbs of different colors. So this is sort of similar to our problem here, except this light bulb here, I don't know, you could debate whether this was orange or yellow, but this probably distributes a wave of orangey yellow light. Our light bulb is only giving out exactly 600 nanometer photons. So this is more like a laser light bulb, one unique wavelength. If you've ever played around with lasers, where my laser at? Lasers like this is like probably 520 nanometers. They give off a very pure electric kind of light that has a very pure color. Now, that means this bulb is emitting only orange photons. The wattage, the power of the bulb is 100 watts. In part A, we are going to find the energy of a single photon. What equation should we use? Wink, wink, you might have just used it.
The same Planck's constant times c over wavelength.
Now, I'm going to play some tricks with you. Normally, I really care about dimensional analysis, but I bet, Ian, that if you were a close payer attentioner, you remember what to do with the nano. You can quickly convert that by doing what?
Just make it 600 times 10 to the negative 9th meters.
Exactly. So that was kind of the cool takeaway from the last problem, is that we can quickly convert that. And that allows us to quickly solve this problem. The Planck's constant is 7 times 10 to the minus 34 joule seconds times the speed of light, 3 times 10 to the 8 meters per second over 600 billionths of a meter. Why don't you guys punch that up?
I got 3.5 to the negative 19th. And
3.5 times 10 to the minus 19. What are your units?
joules.
That's the answer to part A. Okay, Nori, what's part B say?
How many 600 nm photons would have to be emitted each second to account for all the light from this 100-watt light bulb?
They're asking you to calculate a number of photons per second emitted in all directions from that light bulb. Can anyone think of a way to do that? Let's start with the fact that we know that the total power, it's kicking out 100 watts in all directions. The luminosity or the power of a light bulb is its light emission in all directions. And that 100 watts means I'm emitting 100 joules per second in all directions. Let's talk about dimensional analysis level 2. When you don't know what the formula is, a good scientist can often use units to figure out how to solve a problem without even having a formula. This is called dimensional analysis level 2. And I'm going to show you how it works. It's like a little mini game. I want to either multiply or divide two things with the units that I have such that I end up coming out with some answer whose units are photons per second. Can anyone think how to take these units and jiggle them around until you get that?
So would we be measuring the photons as the answer to A, like the joules?
Well, this is the number of joules in a single photon.
Yeah.
So if you want, Ian, you can kind of imagine this as having units of joules per photon. One reason it's okay to slap that in there is photon is a conceptual unit. It's not a real unit. So photons per second are actually kind of the same as 1/seconds. But don't confuse it with the frequency of light. It's not the same thing.
Yeah. Okay. Cool.
So you got joules per second and joules per photon. Let's not worry about numbers. Let's just jiggle around some units until you end up with photons per second.
Okay. So, see, I'm not really sure.
No, you can do this. It's
Okay.
just like mix and match. It's
we would probably want to start with the joules per second, right? The
Good.
100 joules per second.
okay. Now, what units would you need here to end up with photons per second?
Well, we would want to have joules on the bottom for sure.
Yep.
And I guess photons on top?
Yeah. This is how you do dimensional analysis level 2. Okay. Do I know the number of joules per second emitted from the bulb?
Yeah, it's 100 over 1.
That's right. 100 joules are emitted in 1 second. Do I know the number of photons in a joule or the number of joules in a photon?
Well, that would be the energy we just got. So the joule, the bottom part would be the 3.5 times 10 to the negative 19th.
And what's on the top?
1.
Per 1 photon.
Right. Yeah.
So it looks like if we divide 100 joules per second by the energy of 1 photon, that'll tell us the number of photons per second emitted from the bulb. Go ahead and do that. Do you see how dimensional analysis level 2 works? You don't need a formula. You just use units to tell you what to do.
Is it 2.9 times 10 to the 20th power?
Let's give that a good hard round. Let's call it 3 times 10 to the 20th photons per second. All right. I'm erasing this stuff at the top. So this is our answer for A. That's our answer for B. Now, Nori, I want you to read us part C.
Based on your answer to part B, explain why we don't notice the particle nature of light in our everyday lives.
In other words, the question is, why can't I see one photon? Why can't I see an individual photon? Anyone want to throw out or suggest a reason?
This seems a little bit too obvious, but maybe it is right. It's just too small.
You are correct, Ian, that it is too obvious and therefore incorrect.
Yeah.
Let me explain why too small is not a good answer. I will agree with you, Ian, that 600 nanometers is quite small, and most 600 nanometer things cannot be seen with the naked eye. Except with light, it's different, Ian, because if you think about it, all orange light has a wavelength of 600 nanometers. So if 600 nanometers was too small to see, you wouldn't be able to see orange. So too small is not good enough.
Would it be that it's the amount of energy one photon puts off? So
you are good. The other ones that I was expecting to hear is sometimes people say there's too many. That's no good either because there's too many grains of sand, but you can see that. Sometimes people say it's too fast. That's not true either. But Ian, you fast-tracked us right to the correct answer. It's about energy. One photon has a shit tiny little bit of energy, and your eyeball needs like a particular threshold to be stimulated. For instance, if you had a quantum light bulb that only pumped out 1 photon per second, it would have a wattage of 10 to the negative 19 watts. Now, you might be able to see a 1 watt bulb or a 1/10 of a watt bulb, but there's no way you're going to see a bulb that's 10 to the minus 19 watts. It's just not enough energy flowing into your eyeball. So the correct answer, which Ian has discovered, is there is not enough energy in 1 photon for your eye to detect it. And that was nice of you to speed up our final problem there. So in a moment here, I'm going to stop the recording, but I will stay on for a moment to help Nori deal with her problem and anyone else who has problems, whether they be astronomical or otherwise. I will do my best to solve them. I think you guys know that I'm going to be computing midterm grades today, and they'll be posted today, but they probably won't roll over for you to see until tomorrow. Tomorrow, you'll get a letter grade that shows you how your homework percent, your lab percent, and your exam percents mix in together. And you can always hit me up for deets about that if you need to. So one more time, just let everyone look at that, okay? A, B, C. Are you guys good with this stuff? All right, I'm stopping the recording.